In this video, you're going to learn how to solve for projectile problems in a case where the object or projectile is launched at an angle. However, this time it's a little different from the previous video where I discussed projectiles that are launched at an angle with the same starting and end points, because for this one, the starting and end points are not of the same level. So that's the difference from the previous video. And then the problem is, in a carnival booth, you can win a stuffed toy by tossing a coin into a small dish. The dish is placed on a shelf above the point where the coin leaves your hand with a horizontal distance of 2.5 meters from that point. If you throw the coin with a velocity of 6.0 meters per second at an angle of 62 degrees above the horizontal, it will land in the dish. Ignore air resistance. So let's solve for this problem because it can make you richer by winning some stuffed toys in a carnival booth. Kidding aside, well, these are the general problem-solving steps for projectile problems. I'm not gonna repeat them because I've discussed them previously in one of the videos in this playlist. But what I would rather do is to actually go through the actual steps. So let's deal with letter A first. So for the scenario, let's visualize it first. So we have this shelf in a carnival booth, and then there's a dish on the top of the shelf, and then you're supposed to like toss a certain coin. So you're gonna be standing here. You're gonna toss it upward like this, and you have to like make it land on the dish. Then we assume it will be at the center because that's a usual assumption in physics. And then the horizontal distance is 2.5 meters from the point where you release it. So this is where, this is how far it travels horizontally. And then, yeah, so that's 2.5 meters. And then there's an angle that your initial velocity makes with respect to the horizontal. So that's 62 degrees. By the way, in projectile problems, normally the angle of projection is reported or measured with respect to the horizontal axis. So this is how we visualize the problem. Also, let's write down the given in a tabulated format. So what we are solving for letter A is this one. How high is the shelf above the point where the coin leaves your hand? So if this is the point where your hand is and you throw it like this is basically what we're solving for. So not the entire height of the dish, but just this vertical displacement, which is actually exactly the air time or the time when the projectile is airborne. So we can apply our kinematic equations to really determine this height precisely. So d sub x is 2.5 meters. It's just the horizontal displacement of our projectile, which is the coin. And then we also know the velocity when it was launched as a projectile. So that is v naught, or initial velocity is 6.0 meters per second, and the angle is 62 degrees above the horizontal. So it's above the horizontal, that's why it's positive. Take note that this is neither the v sub x nor v sub y. It's the velocity here in this actual trajectory in this curve. So it's this one. That's the v that we're describing in here. However, in our kinematic equations, we actually deal with either x or y velocity at that time. So we need to determine v sub x from there, and we can express v sub x as v naught cosine theta. Meaning to say, guys, you can solve for v sub x by doing v naught times cosine theta, where this theta is just the 62-degree angle that this velocity makes with the horizontal. And then also, we can determine v naught y from there, which is v naught sine theta. So meaning to say, you can determine the vertical component of this initial velocity by doing 6 meters per second times the sine of this angle. So that's it. And again, whenever you're dealing with projectiles that are launched at an angle, your first impulse would be to make sure that you are taking note of the fact that you can determine, or you should determine, the initial horizontal and vertical velocities out of this curved velocity. Okay? Next, implicit given, meaning to say it's not directly stated, but always remember that for the y component of our projectile, the acceleration is negative 9.8 meters per second squared. Be careful, there's a common misconception that if the object is thrown upward, then acceleration should be positive. That is very wrong. It is the velocity or the vertical velocity that is dependent on the movement of the object. For example, if it's going upward, then that's positive velocity. If it's going down, then it's negative velocity. But for acceleration, it does not depend on where the object is going, but rather it depends on what force is causing this acceleration. So the force causing this acceleration is gravity, and gravity is pulling things downward. It's a downfall pull of the earth, to just make it simpler definition wise. So it should be negative. So again, the acceleration is negative regardless if the object is going up or down, because the force causing the acceleration is directed downwards. So that's it. Do not be confused with that. Next, d sub y is the required to find, or RTF, because the vertical displacement of this coin will tell us how high is this part of the shelf, starting from the release point going up to the ending position of our coin. So as you can see, it will give you the approximate height of the shelf. Only this certain part is what is asked in the problem, not the whole height. Next, let's check the inventory of our given variables. So v naught y, we don't know the exact value yet, but at least we know we can get it using this, and we have these variables in place. Acceleration is known as always. D sub y is the required to find. So as you can see right now, time as well as final vertical velocity are the missing variables. So let's write it here. So final vertical velocity is a missing variable because we don't know it and we're not yet aiming to solve for it. And time is also a missing variable because we also don't want to solve for it yet at this point, and we also don't know its value. So the stumbling block would be, what equation do we pick? We have two missing variables, and we are supposed to pick an equation that contains only one specific missing variable. So that means that we don't have enough given in our y-axis, because you end up having two missing variables in your problem, okay? So if you don't have enough given in your y-axis, you go to the x component of your given variables, okay? So let's look at x. We basically have this one main equation for the horizontal motion. So it's d sub x over time, and then for velocity along x. And then v sub x is known. D sub x is also known in the problem. So you have this in the problem. Therefore, you can solve for time. And if you get to solve for time using your x variables, you can use that same time and go back to your y component where the required to find is actually there, right? So that's how it works. Whenever you are lacking some known variables in one component, then you ask help from the other component. So you don't have enough for y, then you go to x and then go back to y afterwards. Okay, because time is actually a common variable between the two, meaning to say whatever time you can determine using x. It also works for y because you're talking about the same thing. It's the same coin we're talking about. It will spend the same amount of time moving along x and y axis, right? So that's the logic behind that. So what we're gonna do now is to solve for time using our x component because y is insufficient. So let's do that. Let's solve for the total air time of the coin using our horizontal equation, or our constant velocity equation. So v sub x equals d sub x over time. Then we cross multiply to isolate time. So you're gonna have horizontal velocity times time equals displacement along x. We divide both sides of the equation by v sub x because we want to isolate time, so we can cancel it, v sub x, and then time equals d sub x over v sub x. Miss, what happened? Why did you replace v sub x with this? Well, simply because to solve for v sub x, you need to do v naught times cosine theta. And if you plug in the given variables, this is the horizontal displacement of our coin, and then initial velocity in this actual trajectory pointing in this curved path is 6 meters per second, cosine 62, because this velocity is launched at a 62-degree angle above the horizontal. So that's it. Then if you do that in your calculator, you are supposed to get time equals 0.888 seconds. I don't want to follow yet any sig fig rules at this point because this isn't our final answer yet. I just want to keep as many sig figs as I can. So it's 0.888 seconds. And then now that we have the time, we can write it down as if it's a given in the problem. And then again, take note that we only solve for time because it will help us have less missing variables in the y-axis. But at this point, we can now go back to our y component because we are looking for the height of the shelf, and the y component is what is exactly needed for that. So let's go back again. In the inventory, we have d sub y is the required to find. So v naught y is known. It's just v naught sine theta, and we can plug something in for that. A sub y, of course, is known. And then time is already known at this point. Now, v sub y is our one and only missing variable at this point. So that is a great thing to happen because that means to say we can just pick the equation which does not contain the missing variable, which is v sub y, and that is this one. So again, if you're getting lost, what we just did is we tried solving for d sub y using y-axis, but we don't have enough given because both time and v sub y were not known. It should only be just one missing variable. So we turned to x and asked for help, and we were able to solve for time using the x variables. Now that we know time, we're going back to the y-axis because we can finally solve for our d sub y because we only have one missing variable that's left, okay? And again, pick the equation which does not contain the missing variable. And the missing variable is v sub y, so we pick this equation, okay? So it's that simple. So our equation is solving for the height of the shelf. We have this. Again, we pick this because it does not contain our missing variable, which is final vertical velocity. Okay, so let's plug in. So d sub y equals, take note, the v naught y is now replaced with this one. So there's nothing bloody. It says here that v naught y is v naught sine theta. So yeah, we just replace it with that, okay? Because that's what we have in our given. So let's plug in the known variable. So v naught is this, 6 meters per second. It's how fast it's going or it's launched in this actual curved trajectory. And then sine 62. So 62 is the angle at which you launch the coin at 6 meters per second. And then do not forget time. Okay, so it's 0.888 seconds. It's the amount of time taken to cover this entire trajectory in the 2.5 meters horizontal displacement. And then plus, okay, so acceleration is this. Do not forget the negative sign. Common mistake made by students, they usually forget to square the time in this equation based on my experience as a teacher. So do not leave it out. And then over to, you're supposed to get d sub y equals 0.84 meters. So it looks reasonable because you are just solving for this part or for this height of the shelf, right? So it makes sense that if it's like less than a meter taller than you and you get to toss a coin, if this is your hand, this is the dish. Yeah, looks sensible to me. Also, in terms of the sign, it makes sense it's positive because displacement along y appears as positive if it is measured above the point of release of the object or the projectile. So this is your vertical displacement in here, and it is above the starting position of the coin, which is here. So that makes sense. Everything looks good. So let's proceed to the next question. So what is the vertical component of the coin's velocity just before it lands in the dish? Okay. So solving for the coin's vertical velocity, that means to say that v sub y would not now be treated as required to find or RTF and not a missing variable. And if you look at the given, it actually looks complete. We know v naught y because of this expression. And then this is a, this is d sub y. And then we also know time. So there's no missing variable, and that means you can just pick any equation as long as you have the required to find there, which is v sub y, right? But my tip is to, as much as possible, pick an equation where you get to avoid using a certain variable that you only solve for. So example, you only solve for d sub y. Well, it's actually 0.84, sorry for this. So it's 0.84, but we would like to avoid using that because you only solve for it. Like in practical perspective, maybe what if you're taking an exam and the d sub y is wrong? You don't want to use it, right? So we'll think of d sub y as a missing variable and pick an equation where you get to use or you get to see v sub y, but you get to avoid d sub y because you're afraid to use something that you only solve for. And that is this equation. So we're going to use this. As you can see, you can solve v sub y using this. And at the same time, you get to avoid having to plug in this d sub y value. That could be wrong, right? Because you only solve for it. So that's just a technique that I always tell my students to do whenever they don't have a missing variable. So that's our equation. Okay, then let's replace v naught y with v naught sine theta. Nothing bloody, guys. It's just that v naught y is equivalent to this. So we replace it with that so we can readily plug in the variables that we actually do know in the problem. Next, initial velocity is 6 meters per second or 6.0. Then sine theta is this. And then acceleration along y is this. And then the time taken to cover that entire length and entire height is 0.888 seconds. And then in your calculator, you are supposed to get negative 3.4 meters per second for the final vertical velocity. Does the answer look reasonable? Yeah, it's not too high nor too low. It's just the velocity or the vertical velocity of the coin as it goes downward to its to the dish. And if you look at the sign, it's negative. Also reasonable for that sign to appear because this is already the downward part of the coin's motion. So the vertical component of its velocity should really be pointing downward. So overall, the answer looks reasonable. So I hope that's clear. Let's proceed to the problem. To the next problem, rather. So for the second problem, you throw a ball from your window 8 meters above the ground. The ball leaves your hand at a velocity of 10.0 meters per second at an angle of 20 degrees below the horizontal. At what horizontal distance from your window will the ball hit the ground? Ignore air resistance. Okay. You love ignoring stuff. That sounds good. Okay. So this is a window and then that's the ground. So you throw a ball. Nothing, you're just having some tantrums maybe. Physics problems too. Okay, so the ball follows this path, most probably, and then it leaves your hand at a certain velocity. Oh, by the way, yeah, this window is 8 meters above the ground, so let's write it there as well. And then with respect to the horizontal, the ball's motion is like 20 degrees below it. We're gonna put a negative sign because it's below the horizontal. I think I mentioned this before. So this arrow represents the velocity of that ball. Okay, let's list down the given in a tabulated format because we're done with the sketch, pretty much. Okay, so first for y-axis, d sub y is negative 8.0 meters. So that's the displacement of the ball along the y-axis. Miss, why is there a negative sign? The problem doesn't have a negative sign. Yeah, because the problem is just describing how tall is the window how high rather is the window with respect to the ground. But in kinematics, guys, take note, displacement is a vector quantity, and it's given a negative sign if it is measured below the starting position of the object that you are analyzing. So if your ball starts from this window and it goes down, that 8 meters, that 8-meter displacement is below the point of release. So it has to be negative, okay? So be careful with the vectors in your kinematic equation. So d sub y is negative if it's below the starting position, okay? Next, we also know that the velocity of the ball is 10 meters per second and the angle is negative 20 degrees. So again, negative because it is below the horizontal axis. Okay, so this is the horizontal axis because your vector is here. This is the main velocity we're looking at and its tail is right there. So this is our imaginary Cartesian plane. This is the x-axis rather. Okay, so the theta is below that. Make it negative. Next, again, this initial velocity is not super useful if you look at the kinematic equations. They either want the v sub x or the v sub y. So later, we're gonna use v naught cosine theta whenever we need to know v sub x. Because if you do v naught, this one, 10, times cosine theta, cosine negative 20, you can get v sub x, okay? And then for v naught y, or initial vertical velocity, we do v naught sine theta. Okay, so initial velocity, still 10, and then, but this time sine, so sine theta. Those are just based on vector resolution techniques, but I'm not gonna go into that because you're supposed to have learned that earlier before you studied projectile. What else you might be wondering, Miss, why are you not putting a naught or the sub-zero thing for x? Simply because v sub x is constant anyway, so I just want to use v sub x in here. But for v naught y, there's initial vertical velocity and there's also v sub y or final vertical velocity. So I want to distinguish the two, so there has to be a naught or zero, sub-zero for the initial vertical velocity. Next, d sub x is the required to find because it says here, at what horizontal distance from your window will the ball hit the ground? So meaning to say, from this level with the window, how long will this ball travel? So that is our required to find. We're allowed to ignore air resistance based on the problem. And anyway, it's just a ball and it's not a really high height for it to like be affected significantly by air. So yeah, we can treat this as a projectile and ignore air resistance. So, and then take note, implicit variable, it's not directly stated in the problem, but acceleration along y is negative 9.8 meters per second squared. Now let's check our inventory of the variables that we have in the problem. So for x variables, that's all we can list. D sub x is required to find. V sub x is represented by this. And then well, we don't know time. And for the y component, so d sub y is known in the problem, same as acceleration. Initial vertical velocity is known. And then it shows here that final vertical velocity as well as time are actually both missing variables. So you see that in here, meaning to say final vertical velocity as well as time are not required to find variables, but also we don't know their value. So we call them missing variable or MV. And then the next thing that we're going to do is try solving for the required to find based on what we have in the problem. So we need to solve for horizontal distance. It's d sub x. But then again, as I mentioned, we cannot readily solve for it because that would be v sub x times time, and we don't know time. And again, rule of thumb, when one particular component does not suffice in terms of known variables, you turn to the other. So example, we need the x-axis because the required to find will depend on that. But because we don't have enough given, we can turn to the y component. Okay, so that's the technique in projectile problems. So if you look at y-axis, you have two missing variables in here, but it's possible for us to treat one particular variable as a required to find. So example, we can treat time as a required to find instead of missing variable, because if we do that, if we try to solve for time, then we can use that same time to solve for the horizontal distance given these x-axis variables or x-axis values, okay? So that's what we're gonna do. And then v sub y will be the remaining missing variable in here. And because of that, we're gonna use this particular equation to solve for time, okay? So let's write it down. So again, this is our chosen equation because the required to find is time, and then the missing variable is v sub y. As you can see, there's no v sub y in here. So this is applicable for our problem. Second thing I'd like you to notice is that this equation is actually a quadratic equation because there are lots of physics problems where you get to cancel v naught y squared. However, because v naught y is sometimes or often 0, but in this particular case, v naught y is actually not 0. There's an initial vertical component for our velocity because of this kind of angle. Therefore, you're gonna have you're gonna have a quadratic equation for this one because of t squared and then this t expression, and the quadratic equation, if you don't remember it, it looks like this. So x is represented by times. You can see ax squared bx plus c equals 0. And then this would be time squared and then time, right? So that's actually similar in terms of the structure. And then afterwards, that means to say that we're going to have to transform or rewrite this equation into this format. And then, of course, those a, b, and x variables should be numbers so we can readily plug them in. So for this particular list of variables, I'd like to solve for v naught y, so it also becomes an actual number that can be readily plugged in to our quadratic equation afterwards. So solving for v naught y, again, it's v naught sine theta, so that's 10 meters per second times sine times the negative 20-degree angle of projection, and you're gonna get negative 3.42 meters per second. So that's the initial vertical velocity of the ball. And then, yeah, that's good because we can readily use it afterwards in our quadratic equation. So moving forward, we're now going to solve for the ball's airtime using our y variables. And then again, this is our chosen equation. It's a quadratic equation where x here is actually time. And then next, we basically plug in the known variables in the problem. So d sub y is negative 8.0 meters. V naught y is negative 3.42 meters per second. Time is the required to find, so it remains as t. And then the plus sign, acceleration times y is this, and then time squared, okay, over 2. Now, we can simplify this further. So negative 9.8 over 2 would be 4.9. So this is how the equation will look like if you simplify this part of the equation. So nothing bloody. And then next, we need to rewrite this physics equation so that it will be similar in terms of structure to this quadratic equation. Ax squared plus bx plus c equals 0. So again, x here is represented by time. So if you want to have ax squared first, that means to say we're going to have to transpose this negative 4.9 times squared to the left side of the equation. So it will look like this. As you can see from negative, it becomes positive because it moves to the left side of our equation, and this is our equal sign. Next, bx. Okay, so that would be the one with time, okay, because x is represented by time. So again, you transpose this on the left side of the equation, so it becomes positive 3.42 meters per second times time. And then lastly, we have the c. It's the variable which does not go beside any time variable, so that would be 8.0 meters in our equation. So that would be negative 8.0 meters. As you can see, it does not change its sign because originally it's on the left side of the equation or left side of the equal sign, and it's still on the left side, okay? So it's negative 8.0 meter still. And then equals 0. So we're just completing our quadratic equation. So this is now our quadratic equation. What happens next? Tcharin! Okay, since we're solving for the ball's air time, we're gonna use for the quadratic formula. So this is the quadratic equation. We're basically rewriting our physics equation based on this format. And then to solve for the actual time, we need the quadratic formula where x is the time that we are solving for. And as you can see, there are a, b, c variables in there. Nothing bloody. That's just gonna be based on our physics equation, which is this, okay? And of course, this general format of the quadratic equation will help us with that. So our a here is 4.9 because ax squared corresponds to 4.9 t squared in our physics equation. So a there is 4.9 obviously. And then b is 3.42 because b sub x in the general format of quadratic equation corresponds to 3.42 times time because again x is time, okay? And then for the c, that's negative 0.8, okay? 8.0 rather. So that's it. The next thing we do is we plug in those variables in this equation. So negative b is negative 3.42 plus or minus. And then again, b is this. And then negative 4ac is this. So it's just substitution. And then this is 2a in the denominator. Now, take note that in using quadratic formula, you're going to arrive with two answers. So because of the plus or minus expression. So if you use the positive sign or the plus sign and you solve for it using your calculator, you're supposed to get 0.98 seconds for the x. And again, x is time, the one that we're solving for. Okay, so that's one answer. The second answer, if using this quadratic formula, you're supposed to get x or time equals negative 1.7 seconds. That is for the minus sign, okay? So take note that this one is a fictitious answer. So this is negative 1.7 seconds, meaning to say, this refers to a time that took place before the ball was actually let go of the person from his or her hand. That means to say this is not what we are concerned with in the problem because as you can see or recall, what we've been analyzing so far is just like the entire trip of the ball. Once it has become a projectile, once it was let go from the hand of the person. So we don't care or we don't consider the time that took place before the ball was let go from the hand of the person. So the time that we are going to consider to be correct or applicable in this case is the positive answer. So that's 0.98 seconds. And that means to say that that is the total airtime of the ball while it is flying in the air. So that's it. Let's write it down. So that's 0.98 seconds for the time. And then again, going back, you can now go back to the solving the horizontal displacement of the ball. So if you're getting lost, nothing bloody, we started trying to solve for, just a recall, we tried solving rather for the horizontal displacement using x-axis, but we didn't have enough given, right? Because we don't know, we're solving for d sub x, and we didn't even know time earlier, okay? So what we did was we used the y-axis to solve for time. The solution became longer than usual because of the need to use the quadratic equation and the quadratic formula because of, the format of the equation that we came up with. And then we figure out time already. So we can now go back to x-axis and actually solve for our d sub x, which is the required to find. So again, the formula for the constant velocity motion of the horizontal component of the projectile is v sub x equals d sub x over time. So we cross multiply to isolate d sub x. So we're going to have v sub x times time. And then we replace v sub x with v naught cosine theta because that is something where we can readily plug in the known variables, which are this. And then, yeah, so we plug in v naught is this. Cosine theta is cosine negative 20 degrees because negative 20 is there below the horizontal. And then the time taken by the ball to cover this entire trajectory is 0.98 seconds based on our solution using the y variables. So if you use your calculator, or maybe not, don't use your calculator. Your d sub x would be 9.2 meters. It makes sense. It's positive because it is on the right side of the starting point of the ball. So for x or horizontal displacement, it comes out as positive if it is on the right side of your of the starting point of the projectile or the ball in this case. So does 9.2 meters make sense? Yeah, for me it makes sense because considering how high the window is, that's a lot of airtime. So it will really travel far, considering also that the velocity is 10 meters per second. So pretty high. So that's our final answer for this problem. I hope that that has been helpful. Thank you and have a great day.